We'll be doing an introduction to differential equations here. Now a differential equation is any equation which contains derivatives. So dy dx equals x, y double dash plus 2y dash equals negative 3y, and f dash x plus fx equals 1. These are all examples of differential equations. Now the solution to a differential equation is a function or a set of functions, sometimes called a class of functions. Alright, well let's have a look at an example here. We're asked to verify that y equals 2x cubed is a solution of the differential equation 3y minus x dy dx equals 0. Well, let's start off with that equation there. We'll just rewrite that. Now if we take that equation and differentiate, on the left we get dy dx, and the derivative of 2x cubed, that's equal to 6x squared. Now look at what we've got here. We're trying to prove that 3y minus x dy dx is equal to 0. So let's have a look at that left-hand side and work with that. First of all, our 3y. We can see there that y is equal to 2x cubed. So we sub that in and it gives us 3 times 2x cubed. Now we'll minus x times dy dx. And we can see here dy dx is equal to 6x squared. So subbing that in, we're minusing x times 6x squared. Now let's expand that out. 3 times 2x cubed, that's 6x cubed, minus x times 6x squared. So we're minusing 6x cubed. So simplifying now, 6x cubed minus 6x cubed is equal to 0 as required. So we can say therefore that y equals 2x cubed is a solution of 3y minus x dy dx equals 0. Fantastic. Let's have a look at a second example now. We're asked to show that fx equals sine 2x is a solution to f double dash x equals negative 4 fx. Alright, well let's just start off with that basic equation there, fx equals sine 2x. Now let's work with that and we'll differentiate. So our first derivative will get f dash x, and if we differentiate sine 2x, we get 2 cos 2x. Now we need to actually get this and differentiate again, giving us our second derivative. So the derivative of 2 cos 2x, now remember we'll have a minus in here, it's minus 4 sine 2x. Now let's go back to our question. We're trying to prove that f double dash x is equal to negative 4 times fx. So looking at that result there, on the left-hand side first of all, well that f double dash x, we can see over here that that's equal to negative 4 sine 2x. Now looking at that result, the sine 2x here, have a look up the top, fx is equal to sine 2x, so if we sub that in, that's just equal to negative 4 times fx. Now that result we've just got there is exactly what we needed over here on the right-hand side. So the left-hand side equals the right-hand side, so therefore fx equals sine 2x is a solution to the differential f double dash x equals negative 4 fx. Fantastic. Let's have a look at a third example now. We're asked to show that x squared minus y squared equals c is a general solution to dy dx equals x on y. Well, once again, we're going to work with the equation we've been given. X squared minus y squared equals c. Now we're going to get this equation here and rearrange it a bit. That negative y squared, we're going to add that over to the other side of the equation. And at the same time, we'll get that c there and we'll subtract that over to here. So that gives us y squared equals x squared minus c. Now that y squared there, might get rid of that power. So we'll take the square root of both sides here, giving us y is equal to the square root of x squared minus c. Now any time we do differentiating, we don't want things under square roots. So we're going to rewrite that with a power. Remembering a square root is the same as a power of a half, so y is equal to x squared minus c all to the power of a half. Right, well that's set up now, we can start differentiating. So on the left we'll just get dy dx. Now to differentiate here, we use our chain rule or our function of a function rule. You might need to look up that lesson to remember it, but I'll go through it quickly. We bring the power out the front first, so the half. Then the bracket gets written out exactly as it is. Now the power of a half, we're going to take one away from that, giving us a power of negative a half. Now the important bit not to forget, that bracket there, we need to times by the derivative of that bracket. So the derivative of x squared minus c, that's just 2x, so we'll times by 2x. Now we can tidy up a little bit, bring the dy dx down first of all, then we can times out half and 2x together, and that'll just give us x. And this x squared minus c to the power of negative a half. Well, the power of negative a half means it's going to be under a square root, but on the bottom of a fraction. So the negative power moves it to the bottom of a fraction. So dy dx is equal to x over the square root of x squared minus c. Now let's go back to our question. Looking here, we're trying to prove that dy dx is equal to x over y. So looking at that result there, on the left-hand side, first of all, we've got dy dx. Now this dy dx here, well, we just found what that's equal to down here, so let's replace that or sub that in. And then looking at the fraction, we'll see if we can simplify that a bit. We'll get the x first of all, bring that straight down. But on the bottom of the fraction, the square root of x squared minus c, does that look familiar? Well, it should, because it's right there. It's actually what y is equal to, so let's sub y in on the bottom of the fraction. Now x over y, that's what we're working to on our right-hand side, so the left-hand side is equal to the right-hand side. So once again we've proved our result, which means that x squared minus y squared equals c is a general solution to dy dx equals x on y. Fantastic, let's have a look at example 4 now. Now two parts to this question. In part A, we need to show that y equals cx cubed is a general solution to 3y minus xy dash equals 0. And then in part B, we're asked to find the value of the parameter c and state the particular solution given that y1 is equal to 2. Okay, well let's have a look at part A. We're working with this equation here, y equals cx cubed. Now we're working with differential equations, so we'll get that there and differentiate. So on the left we'll have y dash, and the derivative of cx cubed, that'll be just 3cx squared. Now back to our question. We're trying to prove that 3y minus xy dash equals 0. So let's have a look here at the left-hand side. Now the 3y, first of all, we know that y is cx cubed, so we'll sub that in, so 3 outside of cx cubed. And then we're minusing xy dash. And we can see there that y dash is 3cx squared. So we'll sub that in as well. Now let's expand out. 3 times cx cubed is 3cx cubed. Then we'll minus x times 3cx squared. So we're minusing 3cx cubed. We'll have a look at that. Exactly the same expressions subtracted from each other. So that's going to be equal to 0 as required. So therefore y equals cx cubed is a general solution to that differential equation. Now let's have a look at part B. We're finding the value of the parameter c, and we're stating the particular solution, but we're given these conditions here, that y1 is equal to 2. Now that may be written out a little bit differently to what you're familiar with, but effectively what that means is when x is equal to 1, y equals 2. So let's get those two values and we'll sub them into our equation over here, giving us 2 is equal to c times 1 cubed. Now if we work through that, we get the solution c equals 2. So we've got that result there, c equals 2. Well, we're asked to find the value of the parameter c. So that's the first half of the question done. We've just got to state the particular solution now. Well, all that means is we get our value here for c, sub it into this equation, so therefore y equals 2x cubed is a solution to that differential equation. Fantastic. Well, we're going to have a look at a couple of terms now that will be handy for you to know. First of all, the order of a differential equation is the highest numbered derivative in the equation. And then secondly, the degree of a differential equation is the highest power of the highest order derivative. Alright, it might sound a little bit complicated, but let's have a look at a couple of examples here, because they're actually quite easy to work through. So we're asked to find the order and degree of the differential equations. Now our first one, we've got dy dx is equal to 1 plus 0.5 cos x all squared. So finding the order first of all, we just need to look at any derivatives in the equation, and there's only one there, dy dx. Now that's a first derivative. So first derivative means that the order is equal to 1. Now to find the degree, we look at that and see if there's any powers. We see there's no power attached to that, so it's the same as having a power of 1, which means that the degree is also equal to 1. Now in part B, our equation here is f double dash x all squared minus 3f dash x is equal to 2x minus 4. So let's find our order first of all. Well, looking at any derivatives, we can see we've got a couple of them here, a first and a second derivative. Well, this one here, our second derivative, that's the highest numbered derivative. So second derivative means the order is 2. And then to find the degree of that, any powers attached to it, yes, we've got a power of 2 there, so the degree is equal to 2 as well. Now part C, we've got y dash all squared equals 3x squared plus 6. So our order, first of all, looking for any derivatives, we've only got that one there, our first derivative. So that means the order is equal to 1. And then the degree, well, that's got a power of 2 attached to it, so the degree is equal to 2. Now the last question, to 2y dx squared plus 3x is equal to y dx all squared. So let's have a look at our order. What derivatives have we got? We've got these two here, a first and a second derivative. So that's the highest numbered derivative there, our second derivative. So that means our order is 2. Now for the degree, no power there, so the same as having a degree of 1. So it means that our degree is equal to 1. Fantastic, that's the end of our lesson. A lot of stuff covered there. Good work for working your way through all of that. Now all the best as you work your way through your questions.